All right. So this week we looked at two different kinds of arguments, what were called statistical syllogisms and then what are called inductive generalizations. So we looked at some examples of both of those in the video. So I've talked our way through them. These are very common, both in terms of things that you're just going to encounter in the course of your daily life. But they're also sort of things that we use a lot without recognizing that we're using them. So I was thinking about how to introduce statistical syllogisms last night. I sort of was like, actually, why do we trust our memories, right? So if I remember something, why do I assume that it actually happened? And it's probably kind of a statistical syllogism that I'm using, right? Like I have some premise like most of the time what I remember actually happened. So I remembered this thing happening, therefore it actually happened, right? That's a statistical syllogism in effect, right? We're sort of relying upon something being true some percentage of the time and then inferring what's true in a particular case on the basis of the generalization. So the statistical syllogisms are a lot like some of the categorical syllogisms we were looking at earlier in the semester. Again, you sort of have just replace the all with some percentage, right? Some percentage less than 100%. When we're talking about these statistical syllogisms, this is exactly what the problems are going to look like on the exam. You're basically going to have sort of four choices to determine how good the argument is that you're looking at. So first, the conclusion is very likely to be true based on the premises, something like 75%. It won't always be a number, but something like that. Somewhat likely to be true based on the premises, so something like less than 75, greater than 50. And we have statistically unlikely to be true, where there's actually just a less than 50% chance that the conclusion will be true. And then finally, we have one of these new fallacies that we're adding for this week, the fallacy of incomplete evidence. The two fallacies that we're going to talk about this week, students sometimes confuse them. The fallacy of incomplete evidence only occurs with statistical syllogisms. Meanwhile, the fallacy of biased statistics that we're going to talk about, that only occurs with inductive generalizations. So make sure you keep really straight how those two fallacies are different. That's a common thing that I see students sort of get a little bit confused up on the exam, is sort of failing to see how these two fallacies are different. Fallacy of incomplete evidence is, in effect, saying that you did the math wrong. So these first three, you're saying, yeah, the people, when people are calculating their percentage, they calculated the percentage correctly. And then I'm just saying how likely the conclusion is to be true based on the percentage that they calculated. Fallacy of incomplete evidence, this is our non-math way of saying something is wrong with how the percentage was actually calculated. It was calculated incorrectly. And the way in which it was calculated incorrectly, it means we know things about the individual that's being talked about within the statistical syllogism that are not being included in the percentage that's actually calculated. So let's start looking at some specific examples. Let me pause. Anyone have any questions, comments, anything so far? Remember, you can unmute yourself. You can send questions to the chat. All right. So let's start looking at some specific examples. So why don't you look at number one? I've sort of written them up, but try to ignore what I've written up. Try to do it in your own. I basically just didn't want it to be typing in the middle of class. All right. A lot of the time, these are not trick questions at all, right? These are pretty straightforward, right? What percentage of people are we told are in this jail are guilty of a crime? We're told that it's 51.1%. Now, I think that probably makes this the world's worst jail ever invented. That's only slightly more than half of the people incarcerated within it are guilty of a crime. Horrible jail, right? But nevertheless, it still is greater than 50% chance. And so if you're forced to guess, is Joe indeed guilty of a crime or not? Based on what you know, based on all the information about Joe that you have, and what information do you have about Joe? He's in the jail, right? Based on all the information about Joe that you have, you would the only rational thing to guess would be that Joe is guilty, but you'd be really not confident about it, right? Like that's what you'd grudgingly guess if you were sort of forced, right? But it's barely more than a 50-50 chance that he actually has indeed committed some sort of crime, right? So if you were forced to guess, you'd guess it, but you wouldn't be confident. That's what we sort of mean by this sort of somewhat likely, right? it is what the information suggests is probably the case, but not so overwhelmingly that, you'd hold that view particularly strongly. Good so far? All right, do the second one. All right. Again, in this case, it seems like everything we know about Joe, the only thing we know about Joe is that he's in the jail. So it seems like all of our known information about Joe is being included in the percentage, right? Joe is in the jail. Here we have a much better jail, right? 97.5% chance that the person in the jail is indeed guilty of some sort of crime. And so, yeah, again, here you'd say the conclusion is very likely to be true based on the information we have available to us. Right? And you'd be just way more confident. Maybe you make the same guess in 1 and 2, right? But you'd be way more confident about your guess in number 2. There's just a much higher percent chance that Joe is actually guilty. Notice, though, that this is entirely dependent upon the information we know about Joe right now. Right? The only thing we know about Joe right now is that Joe is in the jail. What if I told you that Joe was a warden in the jail? Well, now all of a sudden, right, the percentages are wrong in some sense, right? We wouldn't say that 97.5% of wardens in jail are guilty of a crime, right? This argument only works because the only thing we know about Joe is that Joe is in the jail. If we added in new information about Joe, we'd have to radically recalculate our percentages, recalculate our statistics. If Joe was, let's say Joe was a security guard or something, and we knew that in addition, we would have to reject this argument and say that it completes the fallacy of incomplete evidence. Again, good with number 2? All right. Let's go to the third one then. All right. My hope is that this one, something seems wrong. my hope is that your sense is like, again, maybe you might not have ever put it in these terms that we're putting in today, but if you had heard this argument, you probably would suspect that something was a little bit off with it. Again, this isn't brand new things that you've never done before that I'm teaching you, right? The goal is just to get a little bit more precise about the way you reason all the time, right? What this argument is committing the fallacy of incomplete evidence. Right? We know something about the ambassador from China to the United States besides the fact that he's a person in the People's Republic of China. I mean, it's entirely reasonable that most people, and again, notice it doesn't even have to be a percentage, right? But this is, again, it's something like a percentage, right? Most people in China don't speak English, perfectly reasonable. Yet we suspect that the newly appointed ambassador probably is not representative of the average person in China, right? They're probably way more likely to speak English. Indeed, one might suspect that there's a 100% chance that if a country is appointing an ambassador to the United States, that ambassador probably speaks English. There's a 100% chance of it, right? And so this argument just doesn't do its math right, is the way I want to sort of suggest you think about this fallacy. It didn't calculate the percentage right. It didn't include everything we know about the ambassador in formulating the percentage. And so as a result, the argument is just worthless. It's not that we should say, well, the conclusion probably isn't true. It's just that this argument just doesn't do any good work because it didn't do its math properly. Right? We'd have to start over again, do better math of what percentage of ambassadors speak English, or ambassadors to the United States speak English, right? To have any kind of useful statistical information about how likely it is that the ambassador will or will not speak English. All right. So this is our first example of the fallacy. How are people feeling with it? Any questions? All right. Let's go to, Kaylin, did you have something? No? Okay. All right. Let's go to the fourth one then. All right. My hope is that, again, this one seems pretty off. Again, like nothing subtle going on here. Again, if you saw this in the real world, you'd be probably a little bit confused, right? But what's important is what I wanted to emphasize is the way in which the mistake that's being made here, how it's different from the mistake that's being made in number 3, right? Here, we don't know anything else about you, right? What do we know about you? You're an applicant to the Harvard Law School, right? That's all we know about you. The problem in this case is that the person's just not drawing the correct lesson from the statistical information available to us. Right? They sort of have useful, meaningful statistical information about how likely it is they are to get into the law school. They just draw the exact wrong conclusion from it. Right? They only have a 10% chance of getting in, so the rational thing to guess would be that they're not going to get in, not that they will. Whereas in this case, the problem is a little bit differently. The problem is here that the statistical information just isn't applicable to the ambassador, right? Here, the statistic is applicable, but the wrong lesson is being drawn. So that's the difference between these two cases, between a conclusion just being unlikely to have a true conclusion. We're saying that the percentage is applicable, but they're just drawing the wrong lesson from the percentage. For the fallacy of incomplete evidence, we're saying that the statistics just actually aren't applicable to this individual person who's being discussed. All right, good with 4?
So there's no fallacy. It's just literally the conclusion is unlikely to be true. That's how you would say it? Okay.
That's how you'd say it, yeah. Because there's not really I mean, I guess you could call it like the fallacy of being bad at math or something, right? But yeah, it's not like a special logical fallacy. I mean, maybe you could say the person's thinking that they're going to be an exception when they don't have any good reason to think that they're going to be an exception or something. But yeah, the best way to say this is just that it's just a weak inductive argument. The conclusion's just not very likely to be true, rather than it committing some specific fallacy.
Makes sense.
Awesome, good. Any other questions? This one? All right, so let's turn then to number 5. Right, number 5 is basically just the inverse. And here would just have a good argument, right? It's sort of the exact that indicate the person is reaching the correct conclusion based on the statistical evidence available to them, right? I just wanted to notice that even though the percentage is only 10%, right, we're saying that there's therefore a 90% chance that it won't happen, right? So that's why we're saying, it's still above a 90% chance of being true, even though the listed statistic is sort of 10%. We're sort of taking the inverse of that. That's why we're still saying there's a 90% chance that the person will not get in. Right? Whereas again, like, let's say I gave you another problem. Let's say we know a little bit more about this person talking. So maybe let's say they're the high school debate champion. Right? Then I think we'd want to say, no, we just can't trust this statistic. The statistic's just not applicable because probably high school debate champions are more likely than the average person is to get into Harvard. Right? So here in 4, go back to it, how they're different, right? In 4, we're saying that this percentage is applicable, just that it doesn't lead to the conclusion. Here, we're saying that this statistic just isn't applicable. All right. So let's do one more example of these. So number 6. All right, here again, we've got the fallacy. This is a super weird argument too. Like, again, if you heard this argument in the real world, I think you'd be like baffled by what the person was even saying, right? So let's sort of run it through a little bit. So we're, what's our statistic here? Again, we don't have a percentage, but this overwhelming majority that can sort of stand in for some percentage, right? And indeed, I imagine this is true. Imagine that in most murder trials, the overwhelming majority of people present within the room of where the trial is taking place in are not guilty of the crime. What's our problem? Well, the defendant isn't just any old visitor to the courtroom. Right? The defendant is probably way more likely to be guilty of a crime than the other people who are present, than the prosecutor, than the defense attorney, than the witnesses, than the jury, than any person of the audience, right? The defendant, there's things about the defendant that makes them far more likely to be guilty. Okay. Now, note that we're not by saying that this argument commits the fallacy of incomplete evidence. We're not saying that therefore the defendant is guilty. Right? Again, that's sort of what we're taking place when we say that this 4 was kind of a bad argument. The correct conclusion would be the opposite, right? That's not what we're saying in this case. Right? We're saying that just this argument is meaningless or useless because it didn't calculate its percent correctly. The defendant is not the average person, and so it's true of the average person in the courtroom just as meaningless to figuring out how likely it is that the defendant is or is not guilty. I mean, maybe you could do something like what percentages of all defendants are guilty of crimes or something. Maybe you could do that. That would at least be meaningful information. This just isn't meaningful information at all. This statistic does not apply to the particular case. And so the argument just gives us no useful information. All right. How are we doing with these statistical syllogisms? How are people feeling? The questions are going to look exactly like this on the exam. For the most part, you're not really going to have a lot to sort of defend your answer, really. Particularly if you're just saying like the conclusion's very likely to be true or unlikely to be true. You could almost just like give me what the percentage is or something. Like there's not going to be much to sort of say. The only time where you really do need to do a little bit of explaining is when you're saying that the fallacy of incomplete evidence is being committed. You basically need to tell me what evidence is being excluded, about what's being left out. And so it would be enough just to sort of say this first sentence would be enough for the exam, right? The defendant is more likely to be guilty than other people or something. That would be enough for the exam. These problems are ones you should be able to move through pretty quickly. You'll have maybe 10 or 15 minutes per problem. Or 10 or 15 minutes rather for all of them. All of these problems, like 2 or 3 minutes per problem. Yeah, go ahead.
Well, when we're judging likely, unlikely, is it always just going to be that same range that we have here? The 100 to 75 is very likely, 75 to 50 is likely, somewhat likely, so on.
I'll include that on the exam, but that's exactly right. Yeah, it'll be exactly the same percent ranges. And if you get something like the overwhelming, it'll always be something like the overwhelming majority, where it's supposed to be clear that that's more like above 75% than it is under 75%. So, and they won't always be numbers, but it will be something where it's supposed to be really clear which side it's supposed to fall on.
In general statistical analysis, is that also just kind of like a general rule of thumb that is followed, or does it kind of change up depending on the argument that you're making?
It varies a little bit based on the context. So like, let's say if you think of it like this case again, right? In a legal context, what's the standard supposed to be? It's not, well, I think the defendant is probably guilty isn't the standard, right? It's, I think he's guilty beyond a reasonable doubt that would be the standard. So what percent is that? Is that 90%, 95%, right? I mean, 75, it's probably more, not 75% though, right? 75% is probably not beyond a reasonable doubt. So, and that would be an example maybe of where, the percentage would need to be higher before you were really, really confident in it. So it will vary a little bit. It'll also vary a little bit based on how important the decision is. Okay. Too, I mean, maybe we'll accept a lower percentage more readily if it doesn't matter that much. Whereas, if I was told, sorry, my neck, that's where my brain is right now. If I was told, like, there's a 51% chance you're gonna be crippled for the rest of your life, right? That feels way more to me than it was like there's a 51% chance that you'll still be hurting tomorrow. Right. So again, the sort of like what counts as a lot can change a little bit contextually. Is that helpful? Is that getting at the question?
Yeah. Thank you.
Yeah, absolutely. Good. Any others? All right. So let's now turn to our second kind of statistical argument, what are called inductive generalizations. So these are, again, really common. And even more so than with statistical syllogisms, you could spend an entire statistics class about how to do these inductive generalizations well. This is where we're just really in the math range. You can calculate almost everything. You can calculate how large the sample group needs to be. You can, based on the population, you can calculate exactly how likely it is that there's some margin of error. You can calculate the percent chance that there's something wrong in your argument, even though there is a margin of error. Like you can just actually do astounding things with statistical calculations with these arguments. That's obviously not what we're doing. We're not, doing statistical classes. I'm not going to give you the tools you need to sort of really do good inductive generalizations. Our goal is more going to be literacy, right? When you see an opinion poll, have some idea how they did it, what it means, what their methods were, and maybe so you can notice maybe really egregious mistakes in sampling methodologies. That's what we're sort of going to be looking for in these problems. So again, these look exactly like the problems are going to look on the exam. You're going to be basically asked sort of 4 questions. These will be a little bit longer. You're going to need to write a bit more for these problems. So first, you need to tell me exactly what the sample group is, what the overall population is. Second, you're going to need to describe the sampling method in some degree of detail. There's different ways of doing this, but at least I need to sort of have you sort of clearly state how they ran the survey. And then, was there any kind of margin of error included? Sometimes there won't be one, like number 8. We're going to talk about there's sort of one, but not really. But if there is at least a margin of error present in the conclusion, what is it? And then lastly, identify the argument, evaluate the argument, tell me is it committing any fallacies, and if not, it's probably a good argument, at least for our purposes. Basically, we've got 2 ways of doing your math wrong. That's what the fallacies, again, they kind of mean. We have the hasty generalization fallacy, which we're already knew. We saw that one earlier in the semester. Don't really worry about hasty generalization with these problems. Again, you can calculate exactly how large your sample group needs to be. We're not doing that. So for the most part, assume that I'm giving you the sample group, a large enough sample group. The other fallacy that you should watch out for is the fallacy of biased statistics. This is the one that's the most relevant thing that you should be checking. So when your answer to this question should be, is the sample group representative of the overall population? So if the answer is yes, it's a good argument. If it's not, it's a bad argument. The fallacy of biased statistics basically means no, the sample group is not representative for some identifiable reason. So identifying those 4 things, this is more, so these problems are more going to be sort of like a long paragraph kind of deal rather than the statistical syllogism stuff, which will be a little bit shorter. So any questions about anything so far? Just out of curiosity, just in case, say, maybe you were doing an exam and someone asked you this question as a short answer question. If a argument has a larger margin of error, does that make it a stronger argument or a weaker argument?
Weaker.
Weaker. Everyone agree with weaker? Anyone want to say the opposite? It's actually the opposite. It's actually stronger. That's why I wanted us to talk about that a little bit. Margin of errors work weird. They don't work how people sort of intuitively seem to think that they do. What makes a strong inductive argument? It's how likely is the conclusion to be true. Okay? So if a conclusion is more likely to be true, it's a stronger argument. Okay? Conversely, if a conclusion is less likely to be true, it's a weaker argument. Okay? So that's all basic stuff, right? Here's how that applies to the presence of a margin of error. If I was, so there's 12 of us here right now. If I was to say exactly one of us has a January birthday, how likely is it that I'm right? There's a chance. I mean, I'm a January birthday, so I know there's at least one, right? But it's also possible one of you have a January birthday too, at which point the conclusion would be wrong, right? If you want to put it this way, it's a really precise conclusion. Exactly one of us, right? That's a super precise guess. If I was to say 1 or 2 of us have a January birthday, is it more likely that the conclusion is going to be true? More likely, right? It's not as exact of a guess. Think of it as almost like wiggle room, right? I've left myself more wiggle room to be right at the cost of not being as exacta, right? So it's the larger your margin of error, the less sort of like useful the argument becomes. It makes a less precise prediction, but yet that actually makes it a stronger argument, logically speaking, because that extra wiggle room makes it more likely that the conclusion is true. So keep that in mind when you're looking at these things. If you're going to be super precise, you better have a lot of evidence to justify your precision. Right? The more wiggle room you give yourself, the more likely it is you'll be right. And that's what the margin of error is doing. Right? Of course, if I said 1 to 12 of us have a January birthday, 100% chance, I guess, right? But now it's useless. Right now, I'm not making any useful prediction at all. And so when people are doing these kinds of surveys, they need to sort of balance just how large to make the margin of error, right? The larger they make it, the more likely they are to be right, but the less useful it becomes. That example I used in the video, right? That if in a presidential election, it was, someone's going to, 51% of people intend to vote for this candidate, plus or minus 20%. Almost certainly they're right, but we have no useful information that we can derive from that much wiggle room. All right. So any questions about that? Because that might show up on the exam. So I just wanted to make sure we talked about it. So any questions about that margin of error stuff? All right, so let's look at number 7 then. And I'll give you a little bit longer to do this because there's more steps to it. All right, let's start talking our way through this one. So identify the first thing, identify the sample group. Right? And I really think this is worth doing. I mean, sometimes students leave it out, but I think it's really worth identifying the sample group, and that's why I'm making you do it for the exam purposes. Because basically the only question you should be asking yourself is, how good of a job does this sample group do of representing the overall population? So you should, since that's really the only thing that matters, that's the only question you should be asking yourself, it'll really be valuable to try to make it just really, really clear what that sample group is and what is conversely the overall population, right? Being able to sort of precisely say what both of those things are will just make it way easier to gauge how well what the sample group represents the population. So in this case, our sample group is not just all 3,000 of these adults, because all 3,000 of them didn't respond, right? But at least presumably, we don't know, but I guess it's a very unlikely all 3,000 of them responded. So it's the responders from the 3,000 adults that were randomly emailed and called. Right? Those are the people that we sort of got results from. We don't know exactly how many this is. That would be indeed relevant information, right? If it was only one person responded, then, well, I guess that's impossible. But let's say it was what? How can I get 53%? Let's say it was 100. Let's say it was only 100 people that responded. That's a problem. That's probably less than we'd like, right? But let's assume, but it's at least, but if maybe if it was 1,000 people that responded, that's probably a pretty good number, right? That's probably more than enough to do it, assuming that the sampling method is good. Who are these, who is our sample supposed to represent? all adult Americans, not just voters. It specifies it. It just includes, all adults is the sample, that is the population that we're trying to talk about. All right. So what sampling method was used? So we've got, think of this as the question we're asking, how is this group formed? How did we get this group of people? Right? And we got it using what's called stratified randomness. Right? So the people were sort of selected at random, and then they sort of weighed the answers based on relevant demographics, right? So, we suspect that maybe people who are older will feel one way about Medicare that's different from how younger people feel. Or maybe people who are rich will feel differently about Medicare than people who are poor. Or maybe people in different states will feel differently. Or maybe people who are Republicans versus Democrats will feel differently, or whatever, right? You keep men versus women, whatever demographics you want to throw in there, all fine, right? What makes this stratified randomness is that they sort of weighed the responders based on that demographic information. Right? So they sort of, let's say they only got 10% of people who responded were Republicans, but we know Republicans are something like 35% of the overall population, or whatever people identify as Republicans, or something like 35%. So then that means that, that we count that 10% for 35%, right? We weigh it, right? So that it matches what we know to be true about the overall population as best as possible. And similarly with all the other demographics. This is kind of the best practices. If you can do stratified random sampling, that's your best bet. Because it's random, there's very little risk of bias seeping in from something arbitrary about how the people were selected, because randomness isn't biased, basically. And the stratification means that we don't have to worry as much about just getting really unlikely and say happening to only get 10% of Republicans when 35% of people are Republicans, right? Or only happening to get 10% of Democrats when we know 35% of people are Democrats, or something like that. I don't know the exact, I think slightly, whatever. Right? Where we just get really unlikely with our randomness, we can sort of offset that unlikeliness using stratification. All right, good so far? All right, so our margin of error in this case is the plus or minus 3%, right? Sort of the exact prediction would be 53%. That's what it was in the sample group. But rather than saying exactly 53% of adults, right, our pollsters gave themselves a little bit of wiggle room, plus or minus 3% as their margin of error. And that's usually what people will aim for, is something like 2 to 3%. Because this still seems meaningful. This still seems like probably a majority of Americans seem as if they would be opposed to it, right? Based on this polling data. Whereas, if it was plus or minus 5, all of a sudden you're not sure. Plus or minus 10, who knows, right? So plus or minus 2 or 3 is usually about where pollsters will try to aim. And then the last step is just to evaluate the argument in the whole. How is the argument? Overall, I would say this is a pretty strong argument, right? And what do we mean by that? So, basically you should include this sentence basically in all of your answers. There's good reason to believe that the sampling group will be representative of the overall population because of the sampling method. That's literally the only thing you should be looking at in these problems, right? Conversely, if you think it's a bad argument, it's a bad argument because there's good reason to believe that the sample group will not represent the overall population because of the sampling method. Right. So why? Sort of explain your work, maybe talk your way through why both of the fallacies have been avoided, right? So we don't know exactly how many people responded from these 3,000, but if we assume it's a large enough percentage of them, again, maybe 500 if you're using stratified randomness might even be enough actually to get useful data. But if we assume it's large enough, we're avoiding the hasty generalization fallacy. And the only bias, so the only sort of like risk of us leaving people out, that's what we mean we're talking about bias in this context. How likely is it that we just left people out who need to be included? The only bias in stratified randomness is that we are only looking at people who voluntarily chose to respond to the survey. We didn't, hold people at gunpoint and make them answer the survey. Right? We sort of let people choose whether or not they were going to respond or not. That actually is not a negligible concern. Pollsters are increasingly worried. I'll do it like this. So if you got a random call, what is it? How likely is it that would any of you here actually pick up the call from a phone number you don't know? Would any of you do it? I'm curious. If any of you would, actually let me know. Because I actually would be genuinely.
The only time I respond to a number I don't know is if I'm waiting for a response from somebody.
Yeah, if you're waiting for a call, maybe.
No.
Yeah.
And then it's got to be the right area code. Otherwise, no. Nope.
Yep. I'm exactly the same way. I'm exactly the same way. That's the only time I'll pick up a number I don't know. How about same thing if you're emailed? What are the odds are that if someone emails you a survey, how likely are you to respond to it? Right. So actually, a lot of us are getting left out. Right. And the pollsters are increasingly worried because the polls have been polling for like political candidates in particular has been like not wildly off, but a little bit off. It's been a little bit more off the past couple of years than people would have guessed. And people are increasingly worrying that it's because the people who actually choose to respond to these surveys, to be blunt, might just be a little bit weird. There might just be something like, I don't mean weird in a judgment-y sense. I just mean weird statistically, right? They might be statistical outliers in some sense. Maybe they're people who are more passionate. Maybe they're people who are less passionate, conversely, who don't have, who knows, right? Maybe the people who are sort of super into conspiracy theories are going to be less likely to respond. Who knows, right? But that there might be something a little bit weird, again, statistically, about people who actually do respond to these surveys. And that could be skewing the sample. That we have a sort of bias here. That there's people who would not choose to voluntarily respond are not being included within a survey. Unfortunately, again, sort of holding people at gunpoint, there's not really another alternative to this. Unless I'm going to answer my survey or die, right? I guess that would get a pretty good response rate, but that's not a legitimate option. So while this is worrying, potentially, it's also unavoidable. There's sort of no way around this concern. And so I'd say, since everything else is being done so well, the fallacy of bias statistics is largely being avoided here. And so as a result, looking at a strong argument. Yeah, Tim, go ahead.
So the only way it's going to be a biased statistic is if it's obvious that the pollers have gone out of their way to only go to Kansas or someplace that's going to be very striated in their response.
So, yeah, absolutely. Or let's say they only called people. And let's say they only called people on landlines. They didn't call any cell phones. They only called people on landlines. Because then who's getting called? I think it's my mom, and that's it. That might be it. She might be the only one who still has a landline, right? So yeah, or people who are just in Kansas, or maybe they only polled people who read the Wall Street Journal, right? That's what we sort of mean. Not really just people who voluntarily chose to respond, because again, that's unavoidable. They've systematically excluded some people either deliberately or by accident. My favorite example of this. I believe this was actually a real study that someone tried to do. They sort of randomly tried to get in touch with people who had been in car accidents, and concluded that car accidents weren't that dangerous at all because everyone they had gotten in touch with had survived the car accident. And then I think they recognize their error, right? But what's the problem there, right? The problem is, of course, the dead people aren't going to be responding to you, right? There's a group of people being sort of systematically excluded from the survey. And that's what we mean by bias. We mean because of sort of systematic features of how the survey is being done, certain people are just being excluded who matter. Who might have relevantly different opinions than the people who are being included.
Okay, so 100% of people polled outside of a King Soopers didn't like Safeway would be
exactly.
a bias because.
Yeah, exactly right. Right, because of course we suspect that people going to King Soopers likes King Soopers better than Safeway. Yeah, and that's exactly how you'd explain it too. That's you'd want to say basically exactly that as an explanation of it. Awesome. Good. Any other questions with this one? All right, let's do one last example of an inductive generalization. Let's do number 8, and then we'll end it for the day. All right, let's start talking our way through this case. So again, just identify the sample group and the overall population. So our sample group, we've got these sort of 96 actor or athlete owned restaurants. Okay. Those are the sort of who our sample group is made up of. Our overall population is going to be all restaurants, right? And you could also say all newly opened restaurants. Those sort of mean the same thing in this context. They're not meaningfully distinct because all restaurants were new restaurants at some point. So they would overlap. Maybe, I guess, given the topic, probably new restaurants is maybe a slightly better way of putting it. But all restaurants were new restaurants at some point. So the distinction just doesn't matter. Either would be fine on an exam here. All right. In this case, and here's where we need to sort of identify our sample method a bit more precisely. So here, we're not using stratified randomness. Indeed, we're not using randomness at all. Some kind of selection method is being chosen. The magazine is specifically choosing the restaurants that they're going to look at. Now, that's never the best practices, right? You'd never want to do that if you had other options, but sometimes you don't have other options. Doing the kind of sort of like national that 3,000, 2,000 person stratified randomness survey that a journal like the Wall Street Journal can do that's really expensive. It takes a lot of time. It takes a lot of resources, right? Not everyone is capable of doing that. Sometimes you don't have a choice, but to sort of like choose specific individuals to look at. So in noting that this is the sampling method that's being used and it's not the best practices, that doesn't in and of itself mean that it's a bad argument. Right? All it means is that it's dangerous. There's a risk of some bias seeping in based on the person or the group who's making the selection, right? That either explicitly or implicitly, there's something wrong with the particular people that they're selecting to do the survey on, right? So maybe in Tim's grocery store case, right? That was sort of the problem there. That was also kind of they're selecting the people to check, but they didn't select the right people. They should have checked people outside of Kroger and people outside of Safeway and people outside of, I don't know what other grocery stores are even in this area, but whatever other ones there are, right? Like they needed to pick from a broader range, right? That's the danger here as well, right? That they didn't pick a broad enough range of the bias of the restaurants. And so that as a result, there'll be some sort of, again, systematic bias excluding restaurants that could be meaningfully different from the sample group. Talk about the margin of error in this case. There kind of isn't an explicit one. Right? Nothing's really given. You could sort of maybe say that there is. So the margin of error is the difference between sort of like the exact prediction and any wiggle room you give yourself. So you could say maybe that the difference between exactly 13% safer, which is actually what the math says, right? and quite a bit safer. Whatever that difference is the margin of error, I guess, but that's not a numerical calculation, and we usually mean something mathematical by margin of error. So any questions with the margin of error and how that's working in this problem?
In this problem, would you want us to write that out as you have here?
You could just say no, that there isn't really one. That would be fine.
There isn't one identified kind of situation.
There's not. There just is. At the very least, it's not an explicit one, right? There's no mathematical margin of error given. You can maybe say it, put it that way. There's no mathematical margin of error given. All right. So then our final question, we have to evaluate the argument. And really, so since we've sort of recognized that there is this danger, right? What we're mostly going to be looking at is this danger been realized? Have people avoided it, or is there some sort of systematic bias in this case? And I would say, no, they haven't avoided it. This argument commits the fallacy of bias statistics. Athlete and actor-owned restaurants just aren't representative of all restaurants, right? Why? They've got these advantages. They have various kinds of advantages that make you suspect that a restaurant owned by an actor or an athlete is probably far more likely to stay open longer than a restaurant without those advantages, right? Maybe the fame and wealth of the owner, that probably helps restaurants stay open, right? If the owner can afford to burn money longer, right? Also, maybe actors and athletes probably have large social media presences, so maybe they can advertise better, so on down the line, right? We have every reason to think that because of who we've sampled, we're leaving out restaurants that don't have those advantages, and those restaurants probably are in worse shape than the ones that we did indeed sample. I think actually, like the average restaurant, I think it's something like 50% of all restaurants that actually close within the first 2 years. Like it's a really, so this would be a badly selected sample group. The sample group's not going to represent restaurants that don't have the advantages that these restaurants might. Right? And so therefore, fallacy of bias statistics. Right? There's a systematic error that makes it so that not all restaurants are being included within the sample group. All right. Any questions with any of these inductive generalizations, or with any other problem, for that matter, that we've talked about? Because I'm getting a blazing headache, so we probably don't have much longer today. But Tim, go ahead. I want us to go through any questions, though. Don't worry about that.
So the only reason that last example doesn't hit hasty generalizations because we're assuming 96 restaurants would be large enough sample size to say everything, or to represent the whole. It's just the wrong 96.
Yeah, if they think about it like this, if they had done a better job of picking those 96, they could have.
Okay.
Whereas if they had picked 2, it doesn't matter how good of a job they've done picking those 2. That's just not enough.
Okay.
So you maybe say like the sample for hasty generalization, like the sample group needs to be at least has to be large enough that it can, in principle, contain the diversity contained within the population if you use a good enough method.
So assuming that there's less than 96 different types of restaurants that could exist, and thus it could represent the whole. Like something like that. Yeah, like that, and then not maybe even kinds, but like circumstances. Maybe there's how many different circumstances of restaurants are there? Maybe 30. I don't know, but if you pick that 96 restaurants well enough, maybe that could give you some useful information. Okay.
That's why, again, I'm going to say for the most part, don't worry about hasty generalization for the exam, just because you can actually calculate exactly what that number is. If you know a little bit about your population, you can say how large does it need to be to possibly represent the population with math. You can figure that out. Does that help?
Yeah. So unless it's blatantly obvious on the test, then it's not going to be hasty generalization.
That's right. Yeah. Well, really, it's not going to be hasty generalization. I'll just tell you that. What I'm interested in is you checking for fallacy of bias statistics. We've already talked about hasty generalization. We did that earlier in the semester, right? I mean, what I really want you to look for is the fallacy of bias statistics with these problems. That's the new thing, the interesting thing. How representative is the sample group?
Okay.
I had a quick question.
Go ahead.
In this one, the margin of error was none. Like, if that showed up in the question before where there wasn't an obvious reason to say it wasn't like a great argument, would you kind of discount that as maybe making the argument weaker?
Yeah, certainly it makes it weaker. So yeah, like you're talking about like number 7, for example, right? If number 7 had no margin of error.
Mhm.
Yeah. So yeah, I think that's right. It certainly makes the argument a little bit weaker. Now that might not be the same thing as weak though.
Okay.
Right, like weaker just means the percentage went down. Weak is the percentage went under 50%.
Okay.
So yeah, that's I'd say that's how I'd sort of it definitely does make it so that the conclusion is going to have a harder time being exactly right. But it might not still make it a bad argument entirely. So, and at the very least, it doesn't mean that the argument's committed to fallacy of bias statistics, and it doesn't mean that the argument's committed to hasty generalization fallacy.
Okay.
Neither of those really depend upon the margin of error at all.
Right. Okay.
And if the argument, and maybe this will be helpful too, if the argument does commit the fallacy of bias statistics, make your margin of error as long as you want, it's still a bad argument. You just didn't do the math right. The margin of error can only save you if you did your math right, but it's protecting the risk of just getting unlucky or something. If you did your math wrong systemically, it's a bad argument, whatever else is true about the argument. Does that help?
Yeah. Okay. So really, like the margin of error, while it makes the argument stronger if you have kind of a larger margin of error, if you have like 3% versus no percent, it doesn't necessarily really change what your opinion should be on the argument, right?
Yeah, unless it's like a really borderline case or something. But yeah, like if it was a presidential opinion poll, you should be pretty concerned about someone who doesn't have a margin of error, just because those American presidential elections are so razor edged, right? But yeah, if it's a situation where it's like 75%, yeah, so therefore most Americans are in favor of it, like the lack of a specific margin of error in that case probably doesn't super matter. It's not going to really change you from, yeah, there's a greater than 50% chance that this is true.
Okay. Okay. Thank you.
Yeah, absolutely. Good. Any other questions? All right. Awesome. So hopefully I will be feeling better the next time we talk. Who knows? But hopefully I'll be feeling better and we can do a more normal kind of day. I'm sorry this was a little bit rushed. I hope I was coherent. I hope I was making sense. So just some reminders. So you've got an exam this week. I'm probably just going to make it a little bit shorter to make up for how behind I am on grading. That'll cover material from chapter 6 and it'll cover material from this week. So study up for both of those things for the exam. I'm not going to hold explicit office hours, at least on Wednesday, but you can contact me to make an appointment if you need to go over anything. And we can also, I'm hoping by Friday I'll be feeling good enough or able to sit at a computer long enough that I'll just hold normal office hours on Friday. So I was feeling a lot better yesterday before I fell down a flight of stairs because of the muscle relaxants I was on. So that made things take a little bit of a turn, but hopefully I'll get back to feeling a little bit better and we can by Friday I'll be able to hold normal office hours. All right. Have a wonderful rest of your week, everyone. Again, I hope you had a great spring break and I will talk to you next week. Bye.
Thank you. Bye.
Have a good one.